Anytime.
Okay, before we get started, I promised people...
Hey. Yo, we're on tape here, so...
Before we get started, I promised people emitter followers and why they oscillate. So
You promised to give them each an emitter follower?
it's not enough for everybody. The first ones who grab win.
We win. We win. Okay.
That's why they oscillate. You get A. That's how the real world works. The lecture today is kind of a favorite of mine. It's much shorter than the other ones I've droned on for 2 hours, the last couple of lectures we've had. It's a favorite of mine, and it's a favorite because it addresses an issue that I think is generally not addressed in university level education, or any level education for that matter, and that is, where do ideas come from? You know, you look at something that somebody did, and you say, where did they get the idea for this, and where did they get the idea for that? And the answer is, more often than not, the ideas are lying around on the table. And what's not generally taught at the university level is some appreciation for the history of the technology that you're involved with. There really are very few, if any, courses in this country surrounding history of a given technology, history of measurement, history of circuits, history of anything. And I think part of that is because the general assumption is that newer is better, and everything that's been done before has been blown away by the latest technology. Well, the fact of the matter is there's a relationship between Lord Kelvin's electrometer and floating gate technology. There's a relationship between any modern technology and what's occurred before. And what's really sad is that a lot of very clever interdisciplinary solutions to problems don't happen because people are not aware of what's been done and how to screw it together. Now, the guy who wrote this thesis, which is today's lecture notes, was a very good configurer. Okay? He was the right guy in the right place at the right time, and he had his eyes wide open in terms of what technology was lying around on the table.
I'm keeping this one.
The lecture notes for today's lecture are Bill Hewlett's 1939 thesis. And what Hewlett did is he screwed together a lot of ideas lying around on the table. And in every sense of the word, he got paid for it. If you look at Hewlett's circuit without knowing where the ideas came from, the question will pop into your head, how in the world did this guy ever think of this stuff? You know, there's a configuration, a conglomeration of ideas here. Where did he get them all? Give me the lights, please.
Okay.
This is Hewlett's thesis in capitalist pig form. Okay? He took his thesis after he was done with it, and he made a box out of it, and he sold it. Okay? And this box, circa 1939, is a remarkable amalgam of clever ideas, good technology, excellent execution, heads-up engineering, and capitalism. All of that stuff is screwed together in a very nice way. And if you're not aware of where the ideas came from and how it was that he knew how to screw them together, did he think of them all? Did he dream them up? Where did the ideas come from that enabled Hewlett to build this box? And taking a look at the answers to that question provides a very nice introduction to today's lecture, which is about half about how in the name of God did Hewlett have the intellectual wherewithal to do what he did here, one. And two, we'll take a hard look at the circuit technically, and we'll try and improve it with modern components. We'll sort of take up where Hewlett left off technically. Economically, I don't think we're going to catch him. This is the cover of Hewlett's thesis, dated June 1939. Okay, and the title is A New Type Resistance Capacity Oscillator. If you look at Hewlett's acknowledgement, it's pretty much standard for a kid trying to get his thesis and get out of here. Okay, but right here, look down here. You know, first of all, before he does anything, he acknowledges his professor, which is politically a very wise thing to do.
Here, here.
Trying to get your thesis signed. The last paragraph in here provides a very, very valuable clue. The work of various other authors which has been drawn upon in collecting material for this thesis is sincerely appreciated. Emphasis mine on sincerely. This was Bill Hewlett sincerely appreciating some other authors in June of 1939. And who were those authors? Let's look at the last page of the thesis and see how he was in the right place at the right time. Of course, he cites his professor again first. He's no fool. He wants to get out. Okay. The next author is H.H. Scott, who ended up in the hi-fi stereo business. I'm not quite sure what this paper was about. But author number 3, Nyquist, Regeneration Theory. This paper is a classic. In that paper, it's a landmark paper. Look at the date. It's only 1932. It's a relatively recent paper for Hewlett. In that paper, what Nyquist did is he demystified oscillation. He laid out the conditions necessary to start, support, and sustain oscillation. It was a landmark paper. It was very important. So this is kind of how positive feedback works. You know, people could make things oscillate, and they could build oscillators, and they could build radios with oscillators in them, and they could build regenerative receivers, but Nyquist quantified the whole thing. Very important paper. 2 years later, 1934, Harold Black stabilized feedback amplifier. You notice all these guys are Bell System Technical Journal. You know, now they broke up the phone system. I don't know what they're all doing, but back then they were thinking about good stuff. Harold Black, who came up with the notion for negative feedback, and it is true, on the Long Island Ferry on the way home. Black applied for a patent when he came up with the notion of negative feedback, and the patent was rejected by the patent office as a crackpot idea. So Bell went ahead, very wisely, and published the thing. They gave it away. Why was Black concerned with feedback at all? Well, Bell had a problem. They were laying cables across the ocean, and they needed stabilized amplifiers. They needed gain-stabilized amplifiers. There was no way to do it. Black came up with this notion of negative feedback. Classic paper. So you've got two very important elements here if you're trying to build a good oscillator. This is all about positive feedback. This is all about negative feedback. And you really have to step back in time to look at the significance of those papers. Everybody talks about positive feedback and negative feedback today. They're well understood and they're well quantified. Well, back then they weren't, and these were seminal papers. The fifth reference, Meacham. Meacham took these two ideas and he built an oscillator, a crystal stabilized oscillator, which he called a bridge stabilized oscillator. Meacham's contribution fundamentally was he came up with a way to do a very simple, clever gain control, automatic gain control for an oscillator. Hewlett took these three elements right here that were lying on the table, 1932, 1934, 1938, and screwed them together with one other crucial element, which we'll get into in a few minutes, to build his thesis. Let's go to a modern version of Meacham's circuit, right here. Meacham's problem was how to build a sine wave output. What he was trying to do was build a sine wave output quartz crystal oscillator. He wanted a quartz stabilized oscillator with a sine wave. This is a circuit we looked at much higher frequency a couple of lectures. Excuse me, a couple of lectures ago. Let's just walk through it again. Like any other circuit, the best way to see how it works is to throw half of it away. Let's take the crystal out. So that's gone. What do we got left with the crystal out? We have negative feedback, 100 ohms and 100 ohms, and the positive input is grounded. So what we've got is a gain of 2 grounded. That's what it is. So the output should nominally sit about 0. If I drop the crystal in, I now have a connection from the output back around to the positive input. Now I've got a positive feedback path. What's going to happen? This is a very, very selective high Q element. The thing is going to oscillate at the resonant frequency of the crystal. And if you look with a scope at the output and at this point here, that's just what you see. This is the output of the amplifier. You notice what happens? It kind of slews up, hits the positive rail, goes into saturation, slews back down, hits that rail, goes into saturation. Now this trace, number B here, that's this node. So what you have is kind of a quasi-square wave here driving a high Q filter. So this node here, the harmonics are gone and it's filtered. But Meacham wasn't satisfied with that because he knew if what he wanted was a high-quality sine wave with a low impedance output, he doesn't want this thing to go into sat out here. He wants the gain to be such that in this nominally linear loop here, if there's a sine wave there, there should be a sine wave there, because nominally in a linear system, you want everything in phase. Meacham's contribution, both to solving that problem and to giving Bill Hewlett one of the crucial elements he needed for his thesis and his company, is right here. What's that? It's a light bulb. Let's take a look at this circuit, because it's basically the same circuit as that, except this resistor here, Mr. Meacham has turned into a light bulb. What's that all about? Once again, if we pull the crystal out, this thing has a gain of 100 ohms divided by the impedance of whatever that light bulb resistance is, and the positive input is grounded. So all we've done is replace the resistor down here with a lamp. Now, if I drop the crystal in, I get positive feedback, this thing starts to oscillate. Here comes Meacham's magic. As these oscillations start to build up, the temperature coefficient of tungsten is positive. So as this signal gets bigger, as oscillations start to build, this has a positive temperature coefficient, which means its impedance tends to rise as signal builds up. Well, if that impedance rises, the closed loop negative feedback here, which Nyquist had just so nicely quantified a few years before, the closed loop negative feedback gain around this thing goes down. That tends to make the oscillations, instead of build, decay. You can see what's going to happen. This thing's going to pick a stable operating point such that the gain around this amplifier, controlled by the amplitude of the output, having an effect on this temperature coefficient and hence resistance of this lamp, is going to just support oscillation. The system's going to go linear. This is a one-component automatic gain control loop. And that's what you get. Now what we get at the output of the amplifier, instead of clipped sine waves, is we've got a true linear system here now. Okay, and I'm reading out of a distortion analyzer here. Not bad, about 1.5% worth of distortion. At, in this case, at 20 kilohertz. So that's the magic. That's what gave Hewlett his AGC. Hewlett needed one other element. That's a quartz crystal oscillator. Okay? That's basically, in modern version, what Meacham did. Okay? What Hewlett said was, that's not what the world wants. What the world wants is variable frequency. Hewlett pulled out the crystal, went back in the history books to a dusty old circuit called a Wien bridge. Yeah, there was a Professor Max Wien, and in 1891 he came up with this RC, parallel RC configuration. Resonant frequency F is 1 over 2 pi RC. Well, in 1891, Wien probably wasn't trying to get it to oscillate, because in 1891 he had no source of electronic gain available. What Wien was doing is he was balancing bridges for use in telephone circuits. He was building bridges. And that's what he used the network for, and it promptly became buried till Hewlett picked it up threw out Meacham's crystal and dropped a Wien bridge in there. Actually, in the original HP oscillators, they made the capacitors variable. So now you can tune this thing. You give up the high Q and frequency stability of the crystal, but what you get now is a variable frequency resonant element. This is a figure from Hewlett's thesis. What he's playing with here is which light bulb to use. And what he's trying to figure out here is, here's the impedance of the lamp versus the current through it. So he's looking at the resistance versus current curves of various lamps. And obviously, as you move up in this direction, the gain of your gain control goes up. He's trying to figure out where to park it here. He's screwing around with various light bulbs. Doesn't look like he modeled it in SPICE based on the plot here. This is Hewlett's circuit. This is the original HP oscillator, okay, and this is right out of his thesis. You can see all the elements provided by the authors that he sincerely appreciated. Okay, here's the Wien bridge. So that's one side. He got rid of Meacham's crystal and put the Wien bridge in. Here's the lamp. So that's the other side of the bridge. Here's the output of the oscillator. And where does it go? It feeds back to drive the Wien bridge. There. That's the negative, that's the positive feedback. So this right here amounts to the positive input to the op amp, if you will. And the gain stabilizing feedback, there's a resistor coming down here, tying into the lamp. So there's the bridge right there. There's the top of the bridge. There's the Wien side, the negative input, the positive input to the op amp. Here's the other side of the bridge, composed of this resistor and the lamp going down here to the cathode, which is the negative side of the bridge. The other thing you'll notice is all the ads in the electronics magazines today, and lots of IEEE journals are full of all kinds of claims and wonderful circuits about the new form of operational feedback, current feedback. Well, it's not so new. Here's Hewlett feeding back to a cathode in 1939. That's current feedback, which predated voltage feedback by at least 30 years. What did he get? Well, look at his distortion figures here. Not bad. From about 30 hertz out to about 10 kilohertz. This isn't his oscillator circuit running out of gas, it's his instrument running out of gas, his ability to read. Out to about 10 kilohertz, he's well inside 0.5% delta on distortion. And amplitude flatness isn't too bad either. He's well inside a dB or so. Not bad for that at all, especially when you consider that the lamp cannot tell the difference between amplitude-induced changes in its impedance and ambient temperature changes. As ambient temperature changes, the dissipation constant of the lamp changes, its resistance changes, and it has no way of discriminating that from an output change to which it's supposed to respond to. So the crucial piece of information that's missing here is over what range of ambient temperature was this output flatness plotted. But knowing HP and their fundamental honest integrity with regards to specs, I assume became pretty clean.
Can you go back one slide?
Yeah.
I think it's amazing that it actually works because the current to the lamp is also the DC component.
That's right, and the current
yeah.
through the lamp is very light.
Exactly.
The way, the place, that's why I think that he was so careful about picking the current resistance characteristic, because when you set these circuits up, from a lamp sensitivity point, you want to run the lamp. This is an example of things you'll never find in a book. From a lamp sensitivity point, the most sensitive part of the lamp, where you get the best gain control action, is just below the point where the lamp starts to glow. Because once the lamp starts to glow, that's pure emission, and you don't want that. Okay? So you're right, he had to pick his lamp very carefully. If you just,
I mean, if I would do that, I'd put the lamp only in an AC part. But I suppose the amplitude of the oscillation is high enough as to, I mean, an important component of the DC.
that's right, it is.
So that's why it's amazing because it actually works this way.
It's amazing it worked as well as it did, and I'm sure it's why he spent, if you read the thesis, it's why he spent so much time screwing around with light bulbs to get the right one. Now, just how good are the approaches outlined in Hewlett's thesis? If you take modern components and you build his circuit, how much better can you do? This is a modern version of Hewlett's circuit. We've replaced all of his stuff with an op amp. Here's the Wien bridge. Here's an R and a lamp. I was too lazy to plot these characteristics. I just lined up a dozen lamps and started screwing lamps into this circuit until it did anything at all, and then played around with this value. That's the lazy man's way to find the right lamp, to get the right VI characteristic. If you build this circuit and you just plain turn it on, and luckily enough the lamp that won the Derby was a 327, which is a very, very common aircraft lamp. It's the most common 28 volt, 40 milliamp aircraft lamp. That's easy to get. If you just screw that circuit together and build it, you get very low distortion. I'm running at a kilohertz here. You get 25 parts per million distortion. If you get a little fancier and you try and emulate the ranging oscillator Hewlett built, you can take the same circuit and add frequency ranges to it. So now you can get over 3 decades, just like Bill Hewlett did, you can get 20 to 20 kilohertz in 3-decade ranges. The other thing I do, which HP did in production, is you notice up here, I have what I call the low frequency, low distortion mode and the normal mode. What's that? The only difference is in normal mode I use one lamp here. In the low frequency, low distortion mode I use 4. Why? If you try and run this circuit at high frequency, the frequency coming out of here that this lamp is being asked to average into a resistance is much, much faster than the thermal time constant of the lamp. But if you try and run this lamp at 10 hertz or 20 hertz or 30 hertz, you begin to approach the thermal time constant of the lamp, and you're going to start getting hunting in the lamp. The circuit's too slow. The lamp can't average it. The lamp's too fast at 10 or 20 hertz. So what you do on the lowest range, say down 20 hertz to 200 hertz range, and on the bottom here, you fatten up the thermal time constant. And the easiest way to do that is to add more and bigger lamps. You'll notice there's not only 4 lamps, I've gone to a different number here. That lamp's physically larger. Okay, so I just want a lot of thermal time constant here to be able to average the relatively low frequency here. This is the distortion of the multi-ranging circuit at 10 kilohertz, and again you end up with about 30 parts per million. You can see a little bit of crossover, and what appears to be the waveform of 2F. And I can tell you right now, whenever you build a sine wave oscillator and you look at the distortion that rolls out, leading the parade is 2F. That's always the case. Regardless of the mechanism, 2F is the leading offender. This is an interesting plot. This plots the normal mode distortion. So that's the little light bulb, one light bulb mode. And this is the low frequency, low distortion mode, which is the big light bulbs and lots of them. And just what you'd expect is what happens. If we go with a little light bulb that begins to run on a time constant, right around 2 kilohertz, the distortion begins to climb. If you use lots of big lamps, you can push the distortion back down at low frequency. That is explainable. That we can understand. What's going on out here? See right here, we go into the flat and very low distortion numbers. And then the thing begins to walk upstairs out here. What's all that about? I mean, clearly I can win this battle by going to longer time constants. But what's going on out there? Why does it rise at higher frequencies? In order to investigate that effect, I decided I had to be able to have fine vernier control over the AGC time constant. That meant the lamp had to go. This was my first cut at getting rid of the lamp. You can see the outline. So the name of the game now is to be able to have lots of control over that time constant. What I'm going for here is I'm going to try and beat this thing down on distortion. So I want handles on everything. I want to be able to play with everything. You can see the outline of the basic circuit up here. That's the Wien bridge up there, as before. The lamp was down in here. Now it's gone. Okay. What do we got? We have an electronic version of the lamp. And the way it works is, in this case, we sample the positive output peaks of the sine wave. We compare them with a voltage reference. We average, so this is going to set our averaging time constant right here. We average the difference between some DC reference and the positive output peaks of the sine through this big time constant. And then we use this FET to set the negative gain of the amplifier. What do we get for our trouble? What we've successfully done is increase distortion by a factor of 50. So we replaced one little old light bulb with 15 electronic components and made the circuit worse by a factor of 50. So much for modern technology's contributions. Why? What's going on in this circuit that unleashes such a dragon to kill 30 parts per million distortion from a simple light bulb into 50 times worse numbers with all this electronic garbage in here? Where's the billing? This is a device level problem, all you IC people. Somebody said something. Give me that again?
The FET.
The FET. Good man. Here's the fixed circuit. Can you find the difference? It's right down here in the corner. That's channel modulating. What does that mean? What it means is, in this circuit, I'm using this amplifier's gate voltage to control the resistance of this FET. Well, that circuit will work. The problem is the FET's a fairly symmetrical device. That means the gate to channel voltage sets the impedance of the FET. Well, this point right here is moving in frequency. So the gate to channel voltage is not only set by the DC output of this, it's also set by the instantaneous value of this voltage. The differential between the channel and the gate is a function of this DC level, which we intend, and this point here, which is moving at frequency. Hence, horrible levels of distortion, 2F again, roaring out of this thing. You're 50 times worse. What's the fix? The fix is right here. Instead of simply DC biasing the gate now, I feed back a chunk of this channel drive here back to the gate. I think if you go through all the mathematics, what you find out is if these two resistors here are equal value, in theory, that provides just the right amount of feedback to cancel the channel modulation in the FET, and it's basically controlled by the DC coming through here. When you do that, and you tweak this value very carefully, all the good stuff comes back. Distortion runs down about 18 parts per million. Now you look at that, you feel pretty good, and you say, what would be nice would be to get rid of this trim. In fact, what would be nice would be to come up with a gain control mechanism that inherently doesn't have this problem. It's always nice to be able to trim away a circuit problem. Tweaks are neat. Everybody likes them. It's always nice to turn the knob and see the problem go away. But architecture wins over trimming every time. What you want is a scheme down here that inherently doesn't care about channel modulation effects. That's the ultimate trim, is the architecture requires none. This was a cut at doing that. There's a mistake in this figure, and it's a simple mistake. There should be a ground symbol right there. Just ground that line. Same circuit, basically. Here's the weed bridge on top. I've made a couple of changes. One, just because I was rebuilding the circuit, I decided if we're going for the lowest distortion, one thing I want to do is I want to unload the oscillator amplifier to give it all the open loop gain it can have. So I basically just added a monolithic output buffer here, a power buffer. Not so much to get power out of the circuit as so this amplifier sees just no load at all. I'm trying to get all the open loop gain out of that thing I can. That's the sole purpose for doing this. So this is just a gain of 1 inside the loop, just to make this thing see just no loading at all. I come around here. Here's my resistor negative feedback network. Same AGC network with one change. You notice my frequency compensation in here is a little different. Before, I had what I call grunt compensation. You've just got a huge time constant in the loop. Here I'm getting a little fancier. Big time constant in the loop. But I've got a little bit of lead there. I'm trying to get fast settling here. This is the real meat of the change of the circuit. The FET's gone. This is a lead-driven photocell. So that's the lead is driven by current out of the gain control amplifier. You generate light, that impinges on the photocell and changes its resistance. Why do I want that? Because there's no channel resistance there. There is no channel, okay? There's no coupling of any form, okay? And that concern just drops out. So you build this thing up, you get the same distortion now, you got rid of the gate trim, so that feels pretty good. You've got an architecture that's inherently a little better in that regard. Those lead-driven photocells have other problems. For instance, they have horribly asymmetric slew, which is to say, if you drive the lead on, the photocell responds much faster than going off. So you have this AC asymmetry in your loop, which you're going to have to account for in your gain control time constant. But in terms of the stated objective of getting rid of the channel modulation problem, it did it. You get the same performance. Now you take a hard look at this problem. You're down to 15 parts per million distortion. You can see some of this stuff here, but most of the power in this distortion waveform still looks like it's kind of following a 2F outline. If you want to improve on this number, the key is right there. Where is that 2F getting in? You go back and you stare at the circuit. And suddenly you realize two things. One is, there's a lot of empty space here. You know, this is just crying for something to happen. Okay? There's a, you know, nature abhors asymmetry like this. We want some junk in here. The other thing is, if you go back and look at the circuit in its most elemental form, you notice something else. This is basically the same circuit we're playing with now. We've just made it very fancy. You notice something about this circuit. This is moving at AC, oscillating. This point's moving at AC. After all, that's how the light bulb works. If this point's moving at AC, then this point must also be moving at AC. If you look at the dividing of these impedances here, you realize there's substantial amount of signal at the inputs here when this circuit's running. There's a lot of common mode to this circuit. The amplifier is differencing this signal at frequency. You're asking a lot. This thing's moving at multi-kilohertz, and then the real clue, if I can find it, remember I said this plot was interesting because of this? I'm also saying there's a lot of common mode swing at the inputs here. And I'm chasing an effect that seems to increase with frequency. Now if I go look at the data sheet of the amplifier, look at that. Look what happens to common mode rejection versus frequency. It goes away. I've got a circuit that's very demanding of common mode and frequency. There's lots of signal swing at those inputs, and I'm asking the amplifier to balance it. That's likely to be the villain. Here's the hole. I think I know what the problem is. What's the fix? The fix is I've got to get rid of this common mode swing here. Well, how in the name of God am I going to do that if I'm driving a bridge around the input? The way to do it is to unbolt this bridge from ground here, which unfortunately isn't in the diagram, and drive this end of the bridge out of phase from the amplifier. That's hard to see in this diagram. Let's go back to the simpler one. The only way I can think of to fix this problem. The reason I got a lot of common mode here is because I'm driving the bridge single-ended with respect to ground. So if that point's moving and that's at 0, surely those points are going to move. What I want to do is I want to lift up ground and I want to drive it out of phase from the output. The most obvious way to do that is to invert the output at a gain of 1 and drive this point.
You don't want a gain of half?
Or gain of half, right, because of this. The problem is I'll never match the gain. Let's think about what I really want. I'm doing my causality backwards. If I take the output and invert it and drive this point, I'm doing that to cause these points to end up at 0. That's backwards thinking. I stand at these points and I say, I want to force these points to be 0. So what I want to do is measure the voltage between these points, and as a result of that measurement, drive this point to maintain those points at 0. So here's what I'm going to do. Instead of a hopeless gain matching exercise, I'll fill up that hole with this op amp. Same circuit as before, except I measure this input. I compare it to where I want it to be, which is 0, and I force the other end of the bridge to whatever potential is required, which nominally will be out of phase with this one, so that this point ends up at 0. So now I've got 2 basic loops working in the oscillator. I've got the basic oscillator loop with its AGC, but I've also got a second loop forcing this amplifier to run at 0 volts common mode. I don't have to match any gain. I don't need any resistors at all. It's free. This amplifier is going to do whatever it has to do in its single-minded pursuit to force this input to 0. And the rest of this loop is just going to all follow around that point. When you do that, if that's at 0, then that must be at 0. This end of the bridge ends up at whatever negative swings it has to satisfy this. And bingo. You knock that distortion down right to the noise floor of the instruments we had available. What you see now, my distortion analyzer at home indicated about 9 parts per million, and that's about all I've got at home. You got to go to work where they're not as cheap as I am. They'll spend money on stuff like this. And what you see now is there's still a little 2F left in there. It looks like 2F, but you've knocked it way down to 3 ppm. If you're trying to get a PhD, you'll go dig this out, but you're getting into the noise floor of the analyzer. And I decided, fine, it's about 2 o'clock in the morning, it's time to quit, I'm happy. I went down the kitchen. After I built my oscillator, I went down in the kitchen, made myself some hot dogs. I don't like much junk on my hot dogs, just mustard, ketchup, and a couple of hot dogs. Give one to the dog and one to me. That's what I did after I built my oscillator. Bill Hewlett had other ideas. After he built his oscillator, he and his buddy Dave Packard went out in the garage, put them in some pretty boxes. And the caption here with this slide rule has to be, Bill, isn't there some way we can get rid of this thing? You know, he doesn't like the slide rule. The HP 35 was a long way in the future. So that's what Hewlett did after he built his oscillator. Then they hung out their shingle, and this was not cheap in 1939. 71 bucks. Anybody know what a Chevrolet cost in 1939? I think about $600. Anybody know what tuition at Stanford was in 1939? That'll bring it home. That's it. Short lecture today. Questions? I wanted to keep it short so we can all go out and riot with the soccer people.
What about simplifying that circuit after you've dialed in the nonlinear feedback? The gain stabilizing and going back to something with a long time constant like a thermistor.
You can use long time constants. The problem is if you're building an instrument, when you change ranges and stuff, when you put a big step in, the nice thing about long time constants is you bury a lot of sins in this fat time constant. What's wrong with long time constants is you change ranges or you just turn the thing on. It takes forever to settle. So if you're building an instrument, you don't want to tell the user you have to wait 20 seconds for this thing to settle. You know, when you grab an oscillator off the shelf and turn it on, you don't see things go like that, or you change ranges or put any step function into it. You want it to settle as quickly as possible. In fact, the weak spot in this circuit, the place where I'd go to work on this, you know, if I was trying to make something that like I'd show to the world and be proud of, is just there. This is a very, very simple-minded AGC. You know, because once I figured out the waveforms I kept not discussing in here, this is the AC coupled output of the AGC. And what I concluded was, see the peaks there? Yeah, the AC coupled output of the AGC is affecting the distortion product there. So clearly a fatter time constant is going to help. You want to mush those peaks down. But I was chasing this 2F right there. I never did discuss this, and I should have. I was chasing the 2F. There's some power here due to the fact that some of the AGC AC residue is getting through. But I wasn't going after that. In fact, all through these pictures, you see the AGC getting in. There, and there, and there. But 2F seems to be most of the power. I think in the last one I screwed around with the time constants a little. Yeah, beat that down a little. And I think maybe even there some of it's still getting in. But most of it's still 2F. Other questions?
Which app node is this, Jim?
And the Hewlett stuff on the front end is in no app node. It would have been, but at the time Stanford couldn't find the thesis, so I couldn't get it into the app node. But all this stuff is in app node 43, which actually I think is the next lecture, next Friday. There was some question about whether I was going to make it back from my road trip in time next Friday, but I can tell you I get in Thursday night. So I'll be dead when you get me Friday, but I'll be here.
You were talking
Other
about
question?
being in the right place and putting the right things together. Obviously, that made a good first product.
Made a great first product. They sold a barrel.
But that was only the first product.
That was only the first product. But all it takes, with a mindset like that, how could they lose? You know, somebody who's that good a synthesizer. I mean, the element that's not taught, and I'm not sure you can teach, is how to synthesize. You know, if you're Albert Einstein, you can sit there and look up at the stars and go, something's wrong with Newtonian mechanics. I'm going to have to think about it for a while. Okay? And you just pull Einsteinian physics out of the sky. That's not synthesis. I don't know what you call that. That's Einstein. It's genius. You know, most problems don't require that, and that's good because we don't get too many of those guys. What he did is synthesis, which is you've got this stuff lying around. You've got thermodynamics, you've got these papers, you've got this. There's all this junk on the table. And somehow he figured out how to synthesize this thing, not only a set of good ideas into a clever solution, but a clever solution that people want. Then comes the marketing and the capitalism. People wanted it. So he had two things. One, he had a good first product, but he had that mindset. If you read that thesis, okay, it's got to be one of the shortest bachelor's theses ever written in this school. It's very succinct and to the point. You look at like, this guy has exactly the right mindset. He knows just how to grab the issues of importance technically. He knows just how to put them together, and he knows just what he's going to do it. So even if that hadn't been the first product, there's a good chance they would have found another one. I mean, he had this fantastic asset, okay, his ability to synthesize and configure. And I don't know how you teach that. He just knew how to screw it all together in a technical and marketeering sense. Maybe Terman helped him. Maybe Terman told him what the world needs is sine wave. I don't know where Bill Hewlett got interested in sine wave oscillator. But the thesis, if all technical writing was done like that thesis, most instruction manuals, most theses, and most papers would be an order of magnitude thinner and an order of magnitude better. Other questions? That thesis is a marvel of direct, succinct, to the point, hitting the high points and nailing it. It's beautiful. It's gorgeous. I would have hired that guy. You know, but he had other ideas. Other questions?
How does the distortion on your circuit compare to other circuits of similar complexity?
About the same. If you go out and spend lots of money on B&K or one of those, the bottom end of the world is 3, 4, 5, 8 parts per million in terms of distortion. And nobody in their right mind needs that, except for people testing A to D converters, okay, and certain other stuff. Okay, so there's, you're not going to start another Hewlett-Packard with a 3 ppm oscillator. You know, it's a good circuit exercise, but I wouldn't recommend it as a product now. The other problem is, like I say, that circuit, you can achieve distortion that's as low or lower. That number, as far as I know, at the frequencies of interest is about as low as, you know, I've seen. And it was done for a customer. I mean, we had somebody who needed that. They were testing A to Ds, and so were we. The problem is going from that circuit to a real instrument that meets dynamic range, settling time, you know, and all the real instrument specs. The box is really done. You can buy it, take it out of the box, turn it on, and it does what you want. You know, you've got another 6 months or a year's worth of production engineering before it's a real box.
How about integrated oscillators?
As far as I know, there's no integrated oscillator that'll meet those kind of numbers. Now, is that because you can't make an integrated oscillator that'll meet those kind of numbers, or because there's not enough impetus to build it in terms of money? I suspect the latter. You know, in industry, most things, meaning 99.999%, are driven by money. Okay, you know, certainly where I work, okay, we're not going to get a lot of Nobel Prizes come out of that place. Okay, if you can see a market for an integrated oscillator with 3 ppm distortion, okay, and the market's large enough, I can guarantee you the people I work for will beat the hell out of me to build it. But if you can't, forget it. Other questions?
Telling me Stanford lost the thesis of its largest financial contributor?
Greg will, well, I'm sure they would say we lost the thesis. They'd leave off the crass commercial end of it. But Greg will tell you the inside story. I'll just tell you what I got.
Not on tape, I won't.
Turn it off. I came over here because I wanted to gym this lecture together, and I wanted that for part of the app note. And I also was just kind of curious as to, what did this guy write anyway? You know, I've spent time digging around in the box and I see what he did. What did this guy write? So I came over here and I went into the library and I said, where are the theses? And they tell you where the theses are. And I dug around in there, and you just go through them all and like, gone. So I went to the library and I said, I'm looking for this thesis and I can't find it. Well, if it's not there, you could try over here. So I went over there and dig around, go through the alphabet, gone. Okay. So I went back, I said, it's not there. And She said, well, sometimes they get lost. Okay, so she was right. So I said, well, where would I go? She said, well, if it's not here, you probably can't get it. So then I thought, okay, they don't know where I can go. Who would care? Okay, never mind where I can go. Who would care? So then you start thinking, money. Okay, I'll go to Gibbons' office. He would care. So I went to Gibbons' office and I went in there and I said to the woman, I'm trying to get a hold of this thesis. You know, she said, try the library. I said, I did try the library. She said, they sent you here? I said, no, I came here. I thought you might be able to help me. She said, we don't really handle that here. I said, well, this is Bill Hewlett's master's thesis. Let me see that. Okay, so she looks at it. She says, she was pretty good. She said, give me your name and phone number and I'll call you. Okay, and about 2 weeks later, after I'd given up, I got this call, okay, from this woman. It's in the mail, okay, and it showed up. And I figured, all right, they found it. What I didn't know, and what I've heard pieced the story together, is that basically all hell broke loose, okay, because they couldn't find it anywhere on campus, and I guess Gibbons decided, if somebody wants Hewlett's thesis, it should be here. You know, God damn it, I want it. Yeah, I really should have left a microphone with my name and phone number, you know, to see what happened when they found out just some Joe Schmo walks in off the street and says, I'll put a nickel a page in your Xerox machine. I just want a copy of this guy's thesis. And they couldn't find it.
Where did they get it?
I don't know, you know, but there were no bloodstains on it. They got all the bloodstains cleaned off by the time they sent it to me.
It's not even signed.
You know, I noticed that it wasn't signed, so he may not be a real graduate here. You know? My guess is he was in a hurry enough to get out of here and start building.
You know, we were talking before about not giving honorary degrees, but Jim asked if we could honorary flunk him. I think we could actually do that.
Any other questions? Okay, thanks for coming. And like I said, I'll be dead when I get in here next Friday, but I'll be here. I get in Thursday night at some ridiculous hour from this trip, but I won't go to work. Are we on tape?
Yes.
Shit. I won't go to work Friday. I'll rest up. Bye-bye.